Hello everyone, welcome to the Internship Studios session on AWS networking. So in this session, we'll be having an overview and also do a hands-on session on the different AWS networking services we have, which are AWS VPC, which means Virtual Private Cloud, subnets, its related components like Internet Gateway, NAT Gateway, route tables, uh, and also we'll see how AWS peering works, where we'll connect two VPCs with each other, and we'll also create a transit gateway here. So coming to the most basic question that hits our head, what is networking? So we need to understand before diving on to the cloud networking model we have by AWS, we need to carefully understand what this networking is. So we have the definition. Networking refers to the practice of connecting computers and other devices to share resources and information. So in the context of information technology, networking involves the creation and management of networks, which are interconnected systems that allow communication and data exchange between the devices. So these devices can include computers, servers, routers, switches, and other hardware. So we can take this as an analogy again. Imagine you have a group of friends who love to share photos and stories. So each friend has their own house. So and they also want to stay in touch regularly. So in the world of IT, we can say these houses are like computers, and the friends represent the different devices. For example, computers or any phone device, you can say. So to connect them, what we require is we need to decide to build a network. So we lay down, for example, houses. We can do the roads, connecting roads, right? Roads are like, for example, we can take cables or wireless signals between the houses. So now again, like when one friend takes a photo or writes a story, they can easily send it to another friend's house through these roads. So in this scenario, the roads are similar to the cables or wireless connections in a computer network. So to help organize things, you can set up a central meeting point like a community bulletin board. So this board in the IT world, we can say like we have the concept of router. So what this router does is it helps direct the messages from one house to another efficiently. So again, like as your friends group grows, right, you can realize that you need a central place to store and share common information. So you think of building a clubhouse. So clubhouse in the with respect to networking component here involves the server. So we can it's a place where everyone can keep their favorite photos and stories. So now if someone wants to see a particular picture, they can ask the clubhouse, or in our case server, to share it. Also to make sure that only friends can access the clubhouse or server in our case, we will set up a security guard. So security guard equivalent of networking component is firewalls. uh, Firewall is nothing but which checks if the person requesting entry is indeed a friend or not an intruder. Also, like sometimes we want to make sure our messages are extra secure, especially if we are sharing personal stories. So now we decide to send the messages through a secret tunnel. So tunnel in the sense VPN, which is a virtual private network. So it ensures that our conversations remain very private. So in real world scenario, networking is like creating connections between houses, setting up a central point for efficient communication, establishing a clubhouse for shared resources, and implementing security measures to protect everyone's privacy. So just like in the digital world, these elements what it helps is helps group of friends communicate and share in a mature and organized way, we can say. Coming to the components of traditional networking, what we had previously, actually these concepts hold the base for today's modern cloud networking as well. So first is the devices. The devices may be computers, which is the fundamental devices in a network where data is generated and processed. Next comes the routers. So routers are nothing but devices that connect different networks and direct data traffic between them. So let's imagine like the internet is like a big city and your computer is a small house in that city. So now a router we can say is like a traffic police to that house. So when you want to send or receive something like for example pictures, videos or emails from the internet, the router helps direct the information to the right places. It's like the traffic cop guiding cars on the road so that they don't get lost. So the router manages the flow of data, making sure that the pictures you send or the videos you watch reach your computer correctly. It also helps keep the internet connection organized so everything works smoothly, just like a traffic cop keeps the roads running smoothly in a city. So next is the switches. So switches are nothing but devices that connect devices within the same network and facilitate efficient data transfer. So again, like we'll imagine a switch like a magical post office for our devices. So for example, in a big city of computers, each device, for example, we have our computer, printer or gaming console. It's like a house. So now a switch is like a smart post office that helps these houses communicate. So when your computer wants to send a message or a picture to another device, it goes to the switch. So the switch now looks at the address on the message and figures out which house or device it needs to go to. It's like the post office sorting and sending letters to the right addresses. So unlike a hub which was previously used as an older device that just sent messages to all houses, a switch is smart. It only sends the message to the specific house that needs it, making communication faster and more efficient. It's like the post office using a magical map to deliver messages directly to the right doorstep. So a switch helps devices in your computer city talk to each other in an organized and speedy way, just like a magical post office making sure your letters reach the right places. Next important component we have the protocols. The initial one is the TCP/IP, which is the transmission control protocol or the internet protocol, which is the full form of this TCP/IP. So it's a set of protocols that governs communication over the internet. So here let's simplify this TCP/IP. So imagine you are sending a letter to your friend who lives very far away, like someplace XYZ. So in the world of computers, this is like sending information from one computer to another over the internet. So now TCP/IP is like the rules and steps you follow to make sure the letter reaches to your friend correctly. It's a bit like having a very reliable conversation. So first we have the TCP here. So think of TCP as making sure your letter arrives intact. Intact means as it was supposedly sent from the sender. So it's like having a conversation with your friend and asking them to confirm that they received each part of your message. So if something goes missing, you can ask them to fill in the gaps. So this we can correlate with TCP. So next is the IP. So now IP is like the address on the envelope. So what we write, right? For example, we write the owner's name, the street address, the pin code, and any landmarks if that address is having. So it's like IP is like the address on the envelope. So it helps the internet know where to send your letter. So every device connected to the internet, like computers and smartphones, all has its own unique address, which is an IP address. For example, if you go and type in your laptop, for example, go to a browser and just type what is my IP in in Chrome or Edge browser, any browser you can take, and just type what is my IP. So you can see the IP address of your own computer. So it's nothing but when you send a message or letter, for example, in our example, using TCP/IP, it's like having a very reliable conversation with a friend and making sure your message is correctly addressed and complete. So what this helps is it helps computers on the internet communicate effectively, and it ensures your information gets to the right place in one piece. So this is very important in the concept of cloud computing as well, because cloud is nothing but it's all the networking part which is involved. So next important protocol we have is the HTTP here, which is the hypertext transfer protocol. So it's used for transferring web pages on the World Wide Web. We'll break down this HTTP as well. So imagine you are at a restaurant now and you want to order some food. So in the world of computers, this is like your web browser, like Chrome or Mozilla Firefox we have, right? Asking a web page from a server. So now HTTP, which is Hypertext Transfer Protocol, it is the way with which our browser and the server talk to each other during the ordering process. Ordering in our sense means the browsing process. So the first thing that happens is sending a request. For example, in our restaurant, what we do the first thing is requesting food. So we sit at the restaurant table and tell the waiter what you want to eat. So similarly, your browser sends a request to the server asking for a specific web page. Web page can be flipkart.com or any website you are going to search. So the next process is the bringing the food. Bringing the food in our case will be receiving a response from the web page. So the waiter goes to the kitchen, gets your food and brings it back to your table. So in the digital world, the server processes your request, gathers the web page and sends it back to your browser as a response. Next we have is the checking the menu. So similarly we have headers and body concept here in HTTP. So just like a menu might have details about the dish, the response from the server what we get also has two parts, which is headers and body. So headers provide the information about the response and the body contains the actual web page content. Next is enjoying the meal. So the final step after we get the order from the waiter is we eat the meal, right? So next is displaying the web page similarly. So finally we get to enjoy our meal. So in the digital world, the browser takes the web page content received from the server and displays it for you to see and interact with. For example, if we hit flipkart.com, we'll get the response, all the things like whatever the order page we have, the UI we'll get, right? So it's a e-commerce application, so you can try it accordingly. So HTTP is like the language that our browser and the server use to communicate when you're asking for and receiving the web pages. It's the protocol that makes internet a place where you can order and enjoy digital content just like you would order and enjoy a meal at the restaurant. So this is about the HTTP. Next important protocol we have is the file transfer protocol. It is used for transferring files between computers. So you can imagine like FTP, which is file transfer protocol, is like a magical courier service for computer files. So mostly we do the sending and receiving of files, right? Sending will involve uploading of the files. So you put your files in a magic box and tell the courier where to deliver it. So in computer terms, you upload your files to a special storage place on the internet. So another thing is receiving files. So your friend tells the courier where they live and the courier brings the magic box to their door. So in computers, this is like your friend downloading the files from that special internet storage place. So it just eases the sending and receiving of computer files, we can say. Next is the topologies. So there are like four topologies: bus, star, mesh, and ring. Bus topologies devices share a single communication line. Star topology says devices are connected to a central hub or switch. Mesh topology devices are interconnected, providing multiple paths for data. Devices are connected in a circular fashion in the ring topology. So again we'll understand by seeing some examples. So first is the bus topology. So you can imagine a long road which is like a bus where houses which are computers are lined up along the sides. So to talk to each other, the houses send messages down the road. So road means a bus here and houses means computers. So easy communication. So what happens here is there's a very easy communication here. So but if the road gets blocked, for example, there are some issues with the main cable, it can slow down the whole system. That's the issue with the bus topology. Next is the star topology. So we can picture a bunch of houses. Houses here means computers, which are all connected to a central meeting point. So the central meeting point in our case can be hub or a switch. So when a house wants to talk to another, they go through the central point. So if one house has a problem, it doesn't affect the others directly, making it robust. This was about the star topology. Next one is the mesh topology. So we can think about it as a group of friends in a circle. So each friend is connected to every other friend. So if one friend wants to share a message, they can pass it directly to the intended friend. So it's highly connected, great for reliability, but it can also get complicated and needs more cables here. So next is the ring topology which we have. So we can envision it as a circle of houses. Houses means again like computers where each house is connected to two neighbors. So if a house wants to talk to another, the message goes around the circle until it reaches the right one. It is simple topology, but if one house has a problem, it can disrupt the whole circle. So in simple terms, we can say bus is like a single road, star is like a hub with houses around it, mesh is like friends in a circle connecting to each other, and ring is like houses in a circle passing messages around. So each has its pros and cons. So coming to the type of networks, first we have is the LAN, which is the local area network. It says a network that covers a small geographical area like a single building or a campus. So for example, if that network is only catering to a single building, for example, it may be a school, college, or a hospital, we can say that it's a LAN type of network. So next is the wide area network, which also is called as WAN. So it's a network that spans a large geographical area, often connecting multiple LANs. So if you are connecting around a city like city full of networking, then you can say as WAN. Next we have the internet. It is a global network of networks connecting millions of devices worldwide. So a bunch of LANs make WANs and a bunch of WANs makes the internet. So the whole world is connected like this only. We can say that the internet is nothing but there are some cables involved. We'll explore more about in the next slides. Next we need to discuss networking models as well. So the first one we have is the OSI model, which is the Open Systems Interconnection. So it's a conceptual framework that standardizes the functions of a telecommunication or computing system into seven abstraction layers. So we'll see what those seven layers are. It's very important because since we are dealing with the cloud, we need to understand what how internet is working in the back end and how communication between client and servers are happening. Next one we have is the TCP/IP model. So it's a widely used networking architecture again that is based on the internet protocol. So firstly we'll discuss the OSI model. So we'll see from the bottom up approach. First we have the physical layer, which says it transmits raw bit stream over the physical medium. Next we have the data link layer, we have the network layer, we have the transport layer, we have the session layer, presentation layer, and the application layer. So at the bottom of the OSI model we can already see it is the physical layer. So what this layer does is it deals with the physical connection between the devices in the sense the computers. So it's focusing on the hardware aspects like cables, connectors, and the actual transmission of bits over the network medium. So it's, we can say, like the foundation of the building. We can say any construction building we have, it's like the foundation. So it provides the raw infrastructure for all the communication that happens. So next is the data link layer, which is above the physical layer. So this layer is responsible for the framing the raw bits from the physical layer into manageable units called frames. So it also manages access to the physical medium, preventing collisions and ensuring very efficient communication. So we can think of it as constructing a clear path on the road for vehicles to move smoothly. Like road, we can say it's the physical layer, and the vehicles we can say as frames to move smoothly. Next we have the network layer. So the network layer we can say is like the GPS of the OS model. So GPS, we may be having, you may be using the phones, right? GPS is nothing but global positioning system. It helps us know the exact location where we are in. So in the context of network layer, it deals with the logical addressing, routing, and forwarding data packets between the different networks. So this ensures that the data reaches its intended destination regardless of the physical layout of the network. So it actually, as it says, it decides which physical path the data will take. Next we have the transport layer. So above the network layer, the transport layer takes care of end-to-end communication and reliability. So it ensures that data is delivered error-free in the correct order and without congestion. So we can imagine that like a reliable courier service. Courier means which can take your parcels from one place to another, making sure your packages, you mean data, reach their destination intact. Next we have the session layer. So the session layer, it manages and establishes sessions or connections between applications on different devices. So it handles dialog control, meaning it determines when communication begins, when it pauses, and when it ends. So it's similar to orchestrating a conversation between two people, which ensures a smooth and organized exchange of information. So above the session layer, we have the presentation layer. So the presentation layer is responsible for translating the data between the application layer and the lower layers. It deals with data formatting, encryption, and compression, making sure that the data is in a readable format for the application layer. It's like a language translator, ensuring that both sender and receiver can understand the information exchange. At the top of the OSI model, we have the application layer. So what this layer does is it interacts directly with end user applications. It provides network services directly to the user's application software, enabling functions such as email, file transfers, and remote login. So it's comparable to the actual applications you interact with on your computer or device. For example, Flipkart or Myntra or Amazon, whatever the application UI you are interacting with, it will constitute the application layer. So this was all about a brief overview about the OSI model. Next we have is the TCP IP model, which has a total of 4 layers. Uh, the foundation layer here is the link layer, which is a combination of data link plus physical layer. Above that we have the internet layer. Above that we have the transport layer, and at the top we have the application layer. So similar to OSI model, the link layer that we have, it encompasses the hardware components and protocols necessary for transmitting data or a specific network medium such as Ethernet or Wi-Fi. So the network interface layer handles tasks like framing data into packets, addressing and error detection. So above that the internet layer. So above the network interface layer we have the this internet layer here. So it is equivalent to the network layer in the OSI model. So this layer is responsible for again logical addressing, routing and forwarding of data packets between different networks. The internet protocol operates at this layer, so assigning unique IP addresses to devices and ensuring the efficient delivery of data across interconnected networks. So we have some routing protocols such as the BGP and are crucial components of the internet layer, so enabling data to traverse diverse network paths. So we have the transport layer which sits above the internet layer and is responsible for end-to-end communication between devices. So here there are very two key protocols as listed. So we have the TCP, which is the transmission control protocol, and the user datagram protocol, which is UDP. So TCP provides a reliable connection oriented communication by establishing and maintaining a virtual connection between sender and receiver. It ensures data integrity, sequencing, and error recovery. So on the other hand, UDP offers a connectionless, lightweight alternative suitable for applications where real-time communication is more critical than the guaranteed delivery. At the topmost we have the application layer here. So where user oriented communication and network services take place. So this layer corresponds to multiple layers in the OSI model. So including the session, presentation and application layers. So here various application specific protocols operate to enable functions such as email, file transfer, web browsing and DNS. DNS means domain name system. So the application layer serves as the interface between network services and end user applications. So this TCP/IP model, unlike the OSI model, is often considered a very condensed version with the fewer layers. So previously we saw there are 7 layers, here there are only 4 layers. So it has some simplicity and effectiveness which has contributed to the widespread adoption, especially in the context of the modern internet we have. So the 4 layers here work collaboratively to enable reliable, scalable and interoperable communication between devices across diverse networks. So this is about TCP/IP. So next we can see here, this is a very interesting photo of how the internet is connected actually. So whatever we are using the modern internet just with the hit of a phone or smartphone button, it's just the physical cables that we have been connected with each other. So underneath all the oceans we say like these are all the big oceans that we are like Pacific, Atlantic, Indian, Arctic Ocean. So underneath the oceans across the continents and even within the cities, there are an extensive network of submarine and terrestrial cables. Terrestrial means on the land cables that carry data across vast distances. So submarine cables are here. It are laid actually beneath the ocean floor, like around tens of hundreds of meters beneath the ocean. The cables are laid connecting different continents, while on-land cables can run underground. or along utility poles to connect cities and regions. So there are mostly fiber optic cables. So this long distance data transmission is carried out through fiber optic cables. So these cables use pulses of light to transmit data between them, providing very high bandwidth and faster data transfer rates compared to traditional copper cables. So earlier we used to have copper cables like in the pre-internet era. So now it has been modernized with the fiber optic cables. So similarly we have ISPs, which are internet service providers, which come into play. So these are companies that provide internet access to users. For example, we have Jio, Airtel in India, which are ISPs, which help us connect to the larger internet. So they operate data centers and network infrastructure, and they often interconnect with each other to ensure global connectivity. So ISPs use routers and switches to manage data traffic within their networks and to facilitate communication between different networks. So I just wanted to show how like where all the internet is connected with this cable. So this is a map which shows, so you can just research on your own to gain deeper insights, or some YouTube videos on how actually the internet is connected to each other. So we should understand how the internet works again. So first is the devices and endpoints. So devices, we can say computers, smartphones, tablets, servers and other devices with internet connectivity, because there must be something to access that internet, right? So these devices make sure that some we can access the data. Internet is nothing but accessing of data. So next we have the endpoints. Each device connected to the internet has a unique identifier such as an IP address, which is used for routing data. IP is nothing but some specific information which is unique to only that device, so that we can identify some device. So next we have the internet service providers. So ISPs are companies that provide internet access to individuals, businesses and other organizations. There is a variety of technologies including DSL, cable, fiber optic or wireless connections to connect users to the network. So ISPs are nothing but these corporate companies, for example Airtel, Jio, which handle the infrastructure required to help us use the internet. Next we have the local network. At the user level, devices are often connected to a local network such as a home or office network using technologies like Wi-Fi or Ethernet. So these actually LAN, we can say local networks. For example, LAN we have, right? We discussed briefly. So these are confined to a very specific building or a group of nearby building. Actually, these provide very high data transfer rates within the network. This enables quick and efficient communication between devices. It's suitable for tasks like file sharing, printing, and collaborative work, we can say. Next, again, we have the protocols and standards. So, the internet relies on standardized protocols to ensure that devices can communicate with each other. So, the most fundamental protocol is the Internet Protocol, which provides unique addresses for devices and enables the routing of data between them. So other protocols we have, right, TCP, UDP and HTTP we discussed before, are used for specific purposes like reliable data transfer and web communication. Next we have the routing and switching again. So when you send data from your device to another over the internet, it is broken into packets. So router and switches on the internet use the IP address in these packets to determine the most efficient path for the data to reach its destination. So the data can pass through multiple routers and switches across various networks before reaching its final destination. So putting it together, we can see like when you want to access a website or send an email through the internet, so your data goes through a series of routers and switches in the backend. Backend in the sense like behind the like how in the back end it works. For example, we can say the context, the background, we can say. So the routers help your data find its way across the internet, making decisions about the best path to take. So it is about the router's responsibility. So what switches does is switches help direct our data to the specific destination within the local networks, ensuring it reaches the correct device. In essence, routing is like finding the best road between city on a map, and switching is like ensuring letters are delivered to the right houses once they arrive in the town. For example, in a post office perspective, we can say switching ensures that letters are delivered to the correct address. So together, routing and switching make sure our digital information gets from our device to its destination efficiently and accurately on the vast network. So next we have the backbone networks. So high capacity long distance communication links, often referred to as backbone networks, interconnect major regions of the world. So these backbone networks are maintained by large telecommunication companies and internet backbone providers. So backbone network, like it will act as a very core infrastructure, so which enable high capacity and also play a central network role that form the primary connectivity framework for larger networks. So these help in data transmission, connecting various smaller networks and facilitating communication between them. So backbone networks usually play a very crucial role in ensuring the overall efficiency, reliability and scalability of the larger networks. So next we have the data centers. Actually what these data centers do is they also help in functioning and reliability of the internet. So they serve as this very centralized facilities designed to store, process, manage and distribute large volumes of data and applications. So they also are a very key helpers in storage of data, processing huge computing powers, helping with availability and redundancy, content delivery networks. As we have seen, they are a very integral part of data centers. They help distribute content efficiently. So what these CDNs do is there is a very use a network of strategically placed servers to cache and deliver web content such as images, videos, and web pages to users based on their geographical locations. For example, if the user is based in Mumbai, India, then they have a data center which is located to near to Mumbai, and the content will be streamed from that location itself. So it what this does is it reduces the latency and enhances the speed of content delivery. So this is very prevalent in I think OTT platforms like Netflix, Amazon Prime Video. So these types of applications leverage the CDN technology. Also, data centers act as hosting services as well for websites applications. Mm, and in the end, they also help foster cloud computing, capabilities. So coming to the World Wide Web, so it's a system of again interconnected documents and resources linked by hyperlinks and URLs. So for example, browsers Chrome and Firefox are used to access and navigate the web, interacting with web servers that store and serve web pages. Another important concept in networking is the IP addresses and subnet masking. So firstly, IP addressing. So an IP address is nothing but a numerical label assigned to each device participating in a computer network that uses the internet protocol for communication. So it's like having a unique address, unique ID. For example, we have Aadhaar for our uh, self-identification, like for example, every individual has their own ID. So similarly for devices, we have IP addresses. So it serves two primary purposes. So first is identifying the host or network interface, and next is providing the location of the host in the network. So which device or computer to communicate to. So that will identify for that, and also provides the location, means at which place the server or the host is residing in the network. So there are types of IP addresses. So coming to the types of IP addresses, we have two main types here. One is the IP version 4 and the IP version 6. V is small here, so it indicates version. So the Internet Protocol version 4, it's the most widely used IP version. So it consists of four sets of numbers, each ranging from 0 to 255. So it's an example IPv4 address, which is 192.168.1.1. So it's just like an identification. So just like everyone has a name to be identified, so devices on the internet have an IPv4 address to distinguish them from each other. So it's a set of numbers that is very unique to each device. So there are two types of IPv4 addresses again. One is local and global. So local addresses are used within a private network, for example, or Wi-Fi, home Wi-Fi you can say. While global addresses are assigned to devices directly connected to the internet. So whenever your device, for example, your phone connects to the internet, it gets assigned an IPv4 address. So this address helps data find its way from one device to another, just like your home address helps mail find its way to your house. So again, like routers on the internet also use IPv4 addresses to figure out where data needs to go. It's like postal workers using addresses on letters to deliver them to the right houses. So it's again a 32-bit number. So technically each IPv4 address is a 32-bit number. So the four groups of numbers are just a way of representing the longer binary number in a human readable format. So but nowadays what's happening is IPv4 addresses are running out because there are only so many combinations which we can make four groups of numbers. So this is why there's a move towards IPv6 nowadays, which provides much larger pool of unique addresses. So coming to the IPv6, so it's developed to address the exhaustion of IPv4 addresses. It uses a longer address format. So here we can see the address as 192.168.11. It's very short, right? But here we can say it is a long address format represented as hexadecimal numbers separated by colon. So you can say this is a huge format, 2001 colon 0db8 colon 85A3 colon 4 zeros colon. So we can see a long list of address. So from this we can make various permutations and combinations, and thereby billions of IP addresses can be assigned using this format. So the current scenario is that IPv6 is taking lead nowadays due to the exhaustion of IPv4 addresses. So again we have the classes of IPv4 addresses. So within IP addresses also we have different classes. So we have class A, B, C. So class A, it is for large networks with a large number of hosts. So class B is for medium sized networks, and again class C is for smaller networks. So this is the range of IP addresses available within those classes. For example, class A has 10.0.0.0 to 10.255.255.255. So it's a very huge collection of IP addresses that we have. So one good thing is uh, like they actually accommodate very large networks. So with the majority of address space reserved for the network, a single class A address can support up to 16 million host addresses. So that's a very huge number of IP addresses. So again, a significant portion of this class A address space from 10.0.0.0 to 10.255.255.255 is reserved for private networks. So private addresses are commonly used within organizations and are not routable over the public internet. So while some class A addresses are available for public use, so many are reserved for private networks. So this distinction helps in managing the scarcity of IPv4 addresses and allows organizations to use private addresses internally while using a very small number of public addresses for external communication. So this is about class A, and for class B, as we can already see, it's for medium sized networks. Similarly for class C, it's for smaller networks. Again, we have the private and public IP addresses. So private IP addresses are reserved for use within private networks and are not routable on the public internet. Public IP addresses are assigned to devices directly accessible on the internet. So you can see this imagine your uh, think of your home or office as a private club. So everyone inside uses special secret codes. Codes here are IP addresses to talk to each other. So private IP addresses are like this secret codes. So they are used inside your club only. Means the local network for devices to communicate with each other. So common ones here are 192.168.xx or 10.xxx etc. Again, public IP addresses. So imagine like your club wants to order the pizza. So to do that, you need to tell the pizza place where you are. That's your home's address, which is the public IP address. So public IP addresses are like addresses of your homes on the internet. They are unique and the internet uses them to know where to send the information. So inside your club, you use private codes, you mean IP address to chat with each other. But when you order pizza, where you are accessing the internet, your home's address, which means the public IP address, is used. So your home router helps translate between your private codes and your home's public address so that you can enjoy both local and internet communication. So in a nutshell, private IP addresses are for talking inside your club and public IP addresses are like the address you give for things coming from the outside. Outside means internet. So your router helps manage the conversation between these two worlds. So this is about private and public IP addresses. Next, another component is subnet masking. So subnetting is the process of dividing a network into smaller, more manageable subnetworks or subnets. So a subnet mask is a 32-bit number that divides an IP address into network and host portions. So it consists of a series of contiguous 1 bits followed by 0 bits. So the 1 bits in the mask identify the network portion and the 0 bits identify the host portion. So we have an example, the IP address is 192.168.1.1. So the subnet mask is 255.255.255.0 or written in CIDR notation as /24. So in binary we have this format which is followed by ones and zeros. The subnet mask is also combination of ones and zeros. So in this example, the first 24 bits represent the network and the last 8 bits represent individual hosts within that network. So we can say that subnetting is just like organizing houses into blocks in a neighborhood. So the subnet mask helps each house. So each house means each device know which block it belongs to based on its unique address. So again coming to CIDR, which is classless interdomain routing notation. So it's an alternative way of representing IP addresses and their associated routing prefix. Example 192 192.168.1.0/24, where slash 24 indicates that the first 24 bits represent the network. So subnetting allows for efficient use of IP addresses and helps manage network traffic more effectively. It's a crucial aspect of IP addressing, especially in large and complex networks. So we'll simplify CIDR here again. We can imagine that as dividing the city into smaller neighborhoods instead of traditional blocks. Like CIDR uses a more flexible approach to create these neighborhoods. So the CIDR notation, it's a way to express these neighborhoods. So it combines an IP address and a slash followed by a number. For example, we have here 192.168.1.0/24. So breaking down the notation, we have the IP address initially, which is 192.168.1.0. It's like the main street of the neighborhood in a city. So the slash 24, what it tells is, we have this slash 24, it tells you how many houses are in this neighborhood or how many IP addresses. So CIDR allows for a variable sized neighborhoods. So you could have larger neighborhoods or larger IP address ranges or smaller ones. For example, we may have slash 16 or slash 28 as well. So what this does is CIDR helps efficiently manage and allocate IP addresses. It's like urban planning for the internet. So it's allowing for flexible and efficient use of address space. So this is about the CIDR. So we had a basics of all the networking. So now we'll directly jump into the AWS networking. So in the context of Amazon Web Services, networking refers to the set of services and features provided by AWS to enable the creation, configuration, and management of network infrastructure in the cloud. So AWS networking allows users to build and customize their own virtual networks, connect resources within these networks, and establish secure communication between different components of their cloud-based applications. So apart from the traditional networking that we had, so AWS has built its own expertise, the enterprise expertise it has carried forward from many years of research and has packaged something called as AWS Network Services. So we'll slowly deep dive into each of the component. So the first key aspects of AWS networking include the Amazon Virtual Private Cloud. So we can think of AWS VPC has our own piece of the cloud. So you already know what cloud is. It's just like someone else's computer, like someone else's resources. So it's like having your own section in a giant digital playground, we can say. So here a VPC is a private space within the AWS cloud where you can launch your own virtual resources. So resources may be EC2 instance or S3 bucket. It will just give some private space where you can play around and spin up your resources. So it's like just having your own room in a big shared building. So it is just a generic architecture. So this is with the internet connection, public internet through internet gateway. This is like where we can allow the resources to communicate with the outside internet. So we have the region. Region in our case is the AWS region. So a region may be Mumbai or North Virginia in the US. So under that we have this shared space called the VPC, and these are all the other network components. Subnets are nothing but a more fine grained, like just it's like different areas within our room, so it will help us organize and separate things. For example, you might have a corner for the computer or another for the pet, you can say. So under that subnet we have all these instances. Instances means the EC2 instances, we can say. So this under VPC we all have these components. So we need to also see the features of the AWS VPC, what all it can offer us. So first is the user defined virtual network. So users can create and define their own virtual networks, which is VPCs, with a specified IP address range, subnets, and configuration settings. So you can simplify this like a user defined virtual network is nothing but it's like a neighborhood you design. Like for example, if you are planning to design a city, you will design the streets as well, right? So it's just like you have this definition to design the network within the AWS cloud. It's like having your own block of buildings and streets in the digital city. So similarly, we have the components of our virtual network. So just like a neighborhood has houses, parks, and roads, our virtual network here has components like we have the subnets, we have the route tables, and the security groups. So we'll see how we'll configure that in the hands-on session. So these elements will help us shape and secure our digital neighborhood. So we have this subnetting also. So VPCs can be subdivided into smaller segments known as subnets. So subnets are associated with specific availability zones and provide a way to organize and isolate resources. So you can imagine subnets are like different zones in our neighborhood. So you might have a business zone, a residential zone, and a park zone. So they help us organize and separate different types of virtual resources. Next we have the custom IP address ranges. So user can choose their own private IP address range for their VPC, providing flexibility in designing the network architecture. So you can also have the flexibility to choose our designated IP addresses. For example, we can choose from class A, class B, or class C. Any type of IP addresses we can choose. Next we have the internet gateway. So an internet gateway allows resources within a VPC to connect to the internet, enabling communication with external networks. So you can see that the internet gateway is like the main gate of our digital city. It's the connection point between the VPC and the broader internet. So how it works is, so we have inbound and outbound traffic in the VPC. So imagine data traffic flowing in and out of your digital city. So the internet gateway manages this traffic, allowing data to come into the VPC, like users accessing your website, and enabling data to go out, like your application fetching information from the internet. Also, there are like if you have some resources in your VPC that need to be publicly accessible, like a web server, the IGW, which means the internet gateway, allows users on the internet to reach those resources. Again, for resources that should stay private, so the internet gateway helps them access the internet, for example, to fetch software updates while keeping them hidden from the direct external access. It also has like provisioning for public subnets and private subnets. So think of your VPC as having different subnets. So the internet gateway helps data flow in and out of the public subnets where public facing resources are there. Public subnet means where resources inside it are open for the internet. And private subnet means where more sensitive resources are kept, where like there is no internet accessibility for the respective resources. Also, one good thing about internet gateway is it also takes care of the routing decisions. So the internet gateway works with the route tables to make decisions about where traffic should go. So it will dictate like if the destination is the internet gateway knows how to handle it. So if it's within the VPC, the traffic stays within the virtual city as well. So it is very crucial actually for enabling communication between the VPC and the internet. It serves as the gateway for data coming in and going out, managing the flow effectively. So in a nutshell, the internet gateway in AWS is like the main gate of your digital city, allowing data traffic to flow between your VPC and the broader internet. Next, we have the concept of route tables. So users can create and manage route tables to control the routing of traffic within a VPC. This includes defining routes between subnets and to external networks. So again, we'll take the example of a digital city in the cloud. So we can think of route tables as digital maps for traffic within the digital city. So they help us guide data traffic from one place to the another. So there are some components of a route table. So the primary thing is the subnets. So for example, in our digital city, we have different neighborhoods, right? So neighborhoods are nothing but subnets. So each subnet may have different types of resources like public and private areas. So what these routes does is routes are nothing like directions for the traffic. So routes in a route table are like directions for data traffic. So they specify where the traffic should go. For example, if it's headed to the internet, it follows one route. If it's staying within the VPC, it follows another route. So while doing the hands-on session, we'll see how we are associating the route tables and all with the subnet. So how route tables will work is first is the subnet association. So each subnet in our VPC is associated with the route table. It's like saying each neighborhood has its own map in perspective of a city. Next is the decision making. So when data traffic wants to move from one resource to another, example from a web server to a database, the route table helps make decisions. So it looks at the destination and directs the traffic accordingly. Also, in the context of internet traffic versus internal traffic, if the data is going to the internet, the route table directs it to the internet gateway. So if it's staying within our VPC, it routes the traffic internally to the right subnet. So these route tables are very essential for managing the flow of data traffic within our VPC. They help ensure that data goes where it needs to go, whether it's within our VPC or reaching out to the internet. So this is about the route tables. Next is the security groups. Security groups act as virtual firewalls for instances in a VPC, controlling inbound and outbound traffic at the instance level. So you can say that security groups are like bouncers you may have seen in clubs. Any modern club you may visit, there are some bodyguards, people with good physics standing outside. So they decide who gets in and who stays out. So each resource, like a server or a database, has its own bouncer, which is a security group. So there are some like in the working of security groups, we have some rules actually. So each security group has a set of rules, like a list of who's allowed and who is not. For example, a rule could say all traffic from an office, allow traffic from an office but block traffic from everywhere else. So we may have a rule like this. Another thing is resource access control. So when someone or something tries to access a resource, the security group checks its rules. So if the person or thing is on the list, it's allowed in. If not, the bouncer blocks the access. So again, there are couple of inbound and outbound lists. So think of it like VIP lists at a party. So inbound rules control who can come in and outbound rules control where guests can go. So each rule specifies the type of traffic and the source or destination. So these security groups are very crucial in controlling who can access your digital resources. So they add a layer of protection, allowing you to define and manage the traffic coming in and out of your applications and servers. Next we have the network access control list, which are short form for ACLs. So ACLs are stateless rules that control traffic at the subnet level, providing an additional layer of security for VPCs. Again, like NACLs also act like digital checkpoints or police officers controlling the traffic in and out of specific neighborhoods. Neighborhoods mean subnets in our virtual city. So these follow rules to maintain order and security. Next we have the ELB, which is the elastic load balancing. So ELB distributes incoming application traffic across multiple instances to improve application availability and fault tolerance. So whenever the application traffic is coming from users across the globe, so if there are 10 instances, instead of putting load on one instance, it will divert the load equivalently across the 10 instances so that the application is running smooth in the backend. Next we have the concept of Amazon VPC peering. So VPC peering enables direct connectivity between VPCs, allowing resources in different VPCs to communicate with each other as if they were on the same network. So we'll see this in the hands-on demo how this thing actually works. Also we have a couple of other components, which is the VPN and direct connect. So AWS supports virtual private network connections and direct connect to establish secure connections between on-premise data centers and AWS resources. So if you have any private data center built on your own, you can leverage AWS VPN facility and the direct connect facility so that there is data transfer happening between the AWS and the on-premise data center. Next we have the VPC endpoints. So VPC endpoints enable private connections between a VPC and supported AWS services. For example, Amazon S3, DynamoDB without requiring internet gateway traffic. So you can imagine VPC endpoint as a private shortcut that allows your resources to communicate directly with AWS services without going through the public internet. So it actually enhances the resource level communication inside AWS. So when a resource in your VPC wants to communicate with an AWS service, for example, we have S3 for storage or DynamoDB for databases, it usually has to go through the public internet. But with VPC endpoint, you create a direct connection within your VPC to the specific AWS service. So it's like building a private road that goes directly to the service instead of accessing it via the public internet. So unlike the regular route that goes through the city's public roads, for example the internet, the VPC endpoint allows the data to travel privately within the city without ever leaving. So also it is very secure and efficient. So the private route is very secure and efficient here. It's like having a dedicated lane that is faster and safer because it doesn't have to deal with the regular city traffic. For example, there would be some internet congestion sometimes, right? So it will divert that as well. So again, it is very cost efficient and low latency. So because the data stays within the AWS network, it can be more cost efficient and have lower latency compared to sending it out to the public internet and back. So these VPC endpoints are very useful for scenarios where you want to keep your data very secure, avoid the public internet, and have faster and more direct communication with AWS services. Next we have the AWS Transit Gateway. So AWS Transit Gateway simplifies network architecture by allowing interconnection of multiple VPCs, on-premises networks, and remote office locations. So we can imagine Transit Gateway as a central hub. So it's like a major transportation center in a city where different neighborhoods or VPCs can connect. So instead of how it works is, so instead of every neighborhood means the VPC connecting directly to every other neighborhood. or VPC, they connect to the central hub. You mean the transit gateway. It's like having a central bus station where different bus routes converge. Also, it provides a very simplified network architecture. So, transit gateway simplifies the overall network architecture here. Each neighborhood only needs to connect to the central hub, making it more scalable and easier to manage. Scalable in the sense, as and when the number of VPCs connections uh, increase rapidly, so AWS offers scaling options for transit gateway as well. So this is one good point about Amazon VPCs. Again, we have AWS Global Accelerator. So this service improves the availability and performance of applications by utilizing static IP addresses and the AWS global network to route traffic for the optimal AWS endpoint. So, like think of your AWS applications hosted in VPCs as destinations that users want to reach globally. So, AWS Global Accelerator in the context of VPCs is like a high-speed highway specifically designed to optimize the route for users accessing your applications hosted in different VPCs around the world. So, actually, they are designed to optimize the global routing of traffic to your applications, enhancing their availability and performance for users worldwide. Next, we have the flow logs. So, flow logs capture information about IP traffic going to and from network interfaces in a VPC, providing valuable insights for troubleshooting, analysis, and security monitoring. So, natively, it has some logs capturing feature that will help us to troubleshoot any network related issues. Next, we have the VPC endpoints for AWS services. We already saw what these endpoints are. They enable us to privately access the resource. Next, we have the VPC traffic mirroring. So, VPC traffic mirroring enables users to capture and inspect network traffic in their VPC for various use cases, including monitoring and security analysis. So these VPC traffic mirroring is like installing digital surveillance cameras in specific locations of your digital city to monitor and analyze communication between resources. So just as you might place surveillance cameras at critical points in a city, in VPC traffic mirroring, you choose specific locations like between servers or at network gateways to mirror the traffic. So we have the ability to create mirroring sessions. So we set up mirroring sessions to define which traffic to monitor and where to send the mirror data. It's like deciding which camera feeds to watch and where to store the recorded footage. So it is beneficial for troubleshooting, security monitoring, and performance analysis here. It allows us to closely examine the communication between resources within the VPC. So here is an overview of how everything is designed within AWS. So we have the VPC here, which is the AWS Virtual Network. This is the name of the VPC, which is example VPC. We have the CIDR range. It's Amazon provided IPv6 version. Next we have the subnets. So we have two subnets here. One is in US East 2A region and another one is the US East 2B region. Uh, these are like public subnets. Both are public subnets here. And these are the CIDR ranges for their respective subnets. We have 10.0.0/20 and 10.0.16.0/20. Also we have two private subnets as well. So we have these public subnets in the blue box and the private subnets in the normal gray colored box. Next we have the route tables. So since these are public subnets, we have a route table which has 0.0.0.0/0 which is open to the internet. Again we have the network connections here, which is internet gateway. So internet routes to two public subnets, zero private subnets route to the internet. So the two public subnets here are routed via this route table via the internet gateway, we can say. So this was about the overview of how the network is designed within AWS. So next is working with Amazon VPC. So there are like numerous options where we can interact with the Amazon VPC. You can create and manage your VPCs using any of the following interfaces. First one is the AWS Management Console. So what it does is it will provide a web interface that you can use to access your VPCs. So we'll use the AWS Management Console here while doing our hands-on session. Next is we have the Amazon CLI. So it provides commands for a broad set of AWS services, including Amazon VPC, and is supported on Windows, Mac, and Linux. Next, we have the AWS SDKs. So it provides language-specific APIs and takes care of many of the connection details, such as calculating signatures, handling request retries, and error handling. Next, we have the Query API. It also provides low-level API actions that you call using HTTPS requests. So mostly like the things that you need to focus is first is the management console and next is the CLI if you come from a operations background, like for example a system admin kind of work. So you'll be more comfortable with the Linux based or Mac based CLI. So this is a slide from the AWS Summit provided officially by AWS. So how a default VPC looks like. So a default VPC is a VPC which is already created by AWS in advance. So once we log in into our AWS account for the first time, what we have is one VPC is already being created for us. So there are some components. So this is the VPC in whole, the symbol that we have. So under this VPC we have these two subnets. So one is the private subnet here, since there is no access to it to the outer internet. So one here we have this symbol called this inward and outward, which is that it is connected to the public internet through a internet gateway. So these are the CIDR ranges and the respective IP address that the resources have within the subnets. And basically we can see that AZ1 means availability zone. So we have in a region we have the concept of availability zones, which are again separate data centers within AWS. So we have in one subnet in one availability zone and another subnet in another availability zone. Next, these are all the CIDR blocks. We have the 172.31.0.0/16, the CIDR block. /20 is the default subnet. Connected internet gateway. We have the security groups. We have the network access control list as well. So coming to the next concept, important one is the subnets. So after VPC, the main component we observe is the subnet. So subnets are segments of an Amazon Virtual Private Cloud IP address range where users can place groups of resources. So subnetting in AWS VPC allows for better organization, security and resource isolation within the cloud network. So we'll see what are the key aspects of subnets in AWS. The first one is the subnet range. So when creating a VPC, users define an IP address range in CIDR, classless interdomain routing notation. So subnets are then created within this IP address. And CIDR means /20/24 we can say. Next is the availability zones. So subnets in AWS are associated with specific availability zones. So each subnet exists in one availability zone and resources within a subnet are distributed across multiple data centers within that zone for high availability. So we can say that in AWS, subnets are like neighborhoods and availability zones are like separate districts within your digital city. So always placing resources across different subnets and availability zones enhances fault tolerance and scalability for the applications. Next, we have the concept of public and private subnets. So public subnets are typically associated with resources that need direct access to the internet. So they have a route to the internet via an internet gateway. So there is a component called IGW, which is short form for the internet gateway, which we need to associate it with the subnet so that the resources inside the subnet can freely communicate with the outside world. Next, we have the private subnet. So it is used for resources that should not have direct internet access. So they can communicate with the internet through network address translation gateway or NAT instance in the public subnet. So due to some compliance issues, if we have some requirement that the resources should not communicate with the internet, then we can have that possibility of communication with internet by use of a NAT gateway. Again, this is the diagram. We have the VPC subnets and availability zones as well. So you can see it is in the EU West 1, which means it's a European region, and 1A, 1B, 1C are the different available availability zones in that region. So you can see there are three different subnets here with each with a different CIDR range. So here in the first subnet we have the 172.31.0.0/24. Here we can see it's the 1.0 and here we can see the 2.0/24. Here we can segregate the IP address and the respective resources in this availability zones. So after the subnets, one more important thing is routing in VPC. So routing in Amazon Virtual Private Cloud refers to the process of directing network traffic between different subnets, resources, and external networks within the VPC environment. AWS provides several components and features to manage routing within a VPC. So first is we have the route table. A route table contains a set of rules called routes that are used to determine where network traffic is directed. So each subnet in a VPC must be associated with the route table which controls the traffic leaving the subnet. So next we have the main route table. So every VPC is created with a default main route table which is associated with all subnets in the VPC by default. So users can modify the main route table or create custom route tables and associated them with specific subnets. So there is already one default main route table available when you hit inside the default VPC, but we'll see how it goes in the hands-on session about the route tables to understand better. Just understand that we can also create custom route tables as well. So here it says for custom route tables, users can create custom route tables to control the routing behavior of specific subnets. Each custom route table can have its own set of routes, allowing for fine-grained control over network traffic. It says that we can create like n number of route tables, and each route table can have its own set of routes. Means it can have a set path of routes. For example, it's whether it's going to towards the internet or some another VPC. So we can specify fine-grainedly how the routes can be written. Next is the route propagation. So route propagation enables the automatic propagation of routes from a virtual private gateway or VPN connection to the route table associated with the subnet. So this is commonly used when connecting to a VPC to an on-premise data center. So when you are creating a VPC from AWS to a on-premise data center, which means a private data center, then we have the concept of this virtual private gateway that we can leverage. Next is the internet gateway. So internet gateway is a VPC component that allows communication between instances. In our case, the EC2 instances in the VPC and the internet. So to enable internet access for resources in a subnet, a route pointing to the IGW is added to the subnet's route table. So you'll also see this in the hands-on session. Next is the virtual private gateway. So a virtual private gateway is the Amazon VPC side of a VPN connection that enables secure communication with an on-premises network. So routes for on-premises networks are added to the route table associated with the subnet. So this is mostly used in the case of the private data center. So here is a screenshot provided by Amazon, like they were going through a hands-on during the AWS summit. So I have taken for reference. So it says create a route table, delete a route table. So we have the destination, target, status, and propagated. So we can have the under routes, we have the destination side or IP, and the target is local. Local in the sense the traffic is destined for my VPC, stays in my VPC. So it will not propagate to any other VPC here. So all route tables also come with the route table ID. Also explicitly associated means which all subnets it has got associated with. It will show. For example, if you are associated with two subnets, then it will show as two subnets. Again, it says the main route table means yes, it is the main route table, and then we have the VPC ID with which it has got associated. Next important component is the internet gateway. So the internet gateway is a key component in AWS, so that allows communication between instances within Amazon Virtual Private Cloud and the internet. It enables resources within VPC to connect to the internet for outbound traffic and receive incoming traffic from the internet. So in the architecture diagram here, we can see under AWS we have the AWS cloud, VPC we have, the subnet we have, which is a public subnet in a availability zone. We have the public server, in our case a EC2 instance. So in order to communicate with the internet, we have to attach it to a internet gateway. So internet gateway is a component of VPC. So it will act as a kind of a mediator between the outside internet and the internal EC2 instance. We'll also see how to create a IGW in the hands-on session. So the purpose is it serves as a bridge between VPC and the internet, allowing instances within VPC to access internet and be accessed from the internet. Again, it is associated with the VPC. So what this association allows is it enables resources within the VPC to connect to the outside internet. Again, it helps in routing as well. So to enable internet access for resources in a subnet, a route must be added to the subnet's route table pointing to the internet gateway. So this route allows traffic to be directed outside the VPC to the internet. Again, it helps in public IP addresses. So resources in a subnet with a route to the internet gateway can have public IP addresses assigned to them. For example, if you have a EC2 instance connected within them, within the VPC which is connected to internet gateway, then it will have the public IP address. So this will allow them to be directly accessible from the internet. So next is the outbound traffic. So instances in private subnets can access the internet for outbound traffic by routing through a network address translation gateway or NAT instance in a public subnet. So the internet gateway facilitates the return path for the outbound traffic here as well. Next important component is security groups. So security groups in AWS are a fundamental component of the networking infrastructure used to control inbound and outbound traffic to and from Amazon Elastic Compute Cloud instances within a VPC. So here are some key aspects of AWS security groups. First thing is the stateful firewall. Security groups act as a stateful firewall. So if you allow inbound traffic for a specific connection, the corresponding outbound traffic is automatically allowed and vice versa. So how this stateful firewall works is initially it will do the connection tracking. For example, when a packet or for example visitor tries to enter or leave the network, the stateful firewall keeps track of its state actually. It's like the security guard noting who entered the building and from where. Also it will inspect the packets. So unlike a simple packet filter, which is a basic security check, a stateful firewall examines the entire context of a connection. It's like the security guard remembering not just that someone entered, but also the purpose and destination of their visit. Next is understanding the protocols. So the stateful firewall understands different network protocols. It's like the security guard recognizing whether someone is carrying a package or data or just passing through. Also it has dynamic rule adjustments. So based on the context it maintains, the stateful firewall can dynamically adjust its rules. It's like the security guard allowing a person who enter to communicate freely within the building but denying access if they exhibit suspicious behavior. So a stateful firewall provides a higher level of security by considering the context of network connections. So it helps prevent unauthorized access and malicious activities by understanding the state of ongoing communication. Next important parameter is instant level controls. So security groups operate at the instance level, not at the subnet level. So if you have created a EC2 instance, then it will operate that at the instance level. So you associate one or more security groups with each EC2 instance, and the rules defined in these groups apply to that instance. So it's as simple as that. Again, it comes with the default deny all rule. So when you create a new security group, it starts with no inbound or outbound rules. So all inbound and outbound traffic is denied until you explicitly add rules. Rules in the sense, if I want to allow all internet traffic or deny internet traffic, unless I mention it explicitly under the security group, it will not uh, be actionable. So it will deny all the rules by default. So next we have the inbound rules. So inbound rules control the traffic coming into your instances. So you can define rules based on IP protocols, port ranges, and source IP addresses or other security groups. So protocol means HTTP or HTTPS, port ranges we have 22443 example, and source IP addresses. For example, if I want to allow only my local laptop IP address to enter into that instance, then I can have the facility of that as well. Inbound means incoming traffic. So again similarly we have outbound rules. So the traffic leaving our instances can also be managed using different rules based on IP protocols, port ranges, and destination IP addresses. Also we have the possibility of dynamic updates here. So security groups are dynamically updated. Changes to security group rules take effect immediately without the need to restart instances. So like even if the instance is running, so we can play around with the security group on the fly. Yeah, this is a sample diagram from AWS that they have given. For example, it says allow web traffic on 0.0.0 means open to the internet. So we have created my web server security group under this VPC, and it says allow only my web server. So resources created in this VPC can leverage this security group and have the traffic flow accordingly. So we have the different types of security groups here. We have the inbound rules where they have shown the group name is my web servers, and it states that the inbound rule that they are given is HTTP, protocol is TCP, and the port range is 80, and the source they are given is allow all, means it's open to the internet, we can say. So similarly we'll be configuring this in the AWS console. One more important differentiator, also like important for the exam point of view and the interviews point of view, is security groups versus NACL. So you have come this question will be asked most frequently actually to test the knowledge on AWS. So we need to understand that these 3 points are very useful actually. So we have the security group and the network access control lists. So we have the security group which operates at the instance level. Instance level means the resource level, so under the subnet. So but here in network itself we have it operates at the subnet level. It's one hierarchy higher actually. So security group supports allow rules only, but network ACL supports both allow and deny rules. So again this is stateful, where return traffic is automatically allowed regardless of any rules. Network ACL is stateless, so return traffic must be explicitly allowed by rules. So we need to again specify a new rule which must explicitly say that the return traffic must be allowed. So again there are a couple of other things like all rules evaluated before deciding whether to allow traffic. Here rules evaluated in order when deciding whether to allow traffic. Applies only to instances explicitly associated with the security group. Here automatically applies to all instances launched into associated subnets. So it is a subnet level resource, we can say. So next important parameter which will again be playing around is the AWS VPC connectivity. So there's a possibility of connecting your VPCs with each other. So we have like connecting to other VPCs, we have the VPC peering concept, which is the initial one, and next is the transit gateway one. These are the two types of facility we have under the AWS. So first is the VPC peering. It says full private IP connectivity between two VPCs. It says it can peer VPCs across regions, means different regions, for example one with Japan and one. Again it says VPCs can be in different accounts as well. For example, cross account VPC pairing can also be done. If an account, I have personal account in one VPC and my friend has another account and he has created VPC in that account as well. We can also create peering between the two VPCs as well. But one important thing is VPC CIDR ranges must not overlap. So for example, in one account or one region I have given the same CIDR, then it will be very difficult to peer the VPCs. So this is the peering process that happens. So initially a VPC1 will send a peer request to VPC2. It will initiate the peering request. Next we have the accept peering request. So it's a simultaneous thing happening. So VPC1 with VPC2 and VPC2 with VPC1. So there's a two-way handshake kind of thing happening. So here like we have the traffic in the route table where it says traffic destined for the peered VPC. So the CIDR we can say in the VPC1's route table we'll mention the target CIDR of the VPC2, we can say. So it says the PCX, it's kind of an ID that we get after the peering connection is made, and it says active here. Next with transit gateway we have this kind of route table where we get the TGW kind of ID. So here it says the traffic in the route table. We have the traffic destined for any VPC in 172.16.0.0/12 range should go via TGW. So whatever the traffic that is happening within the VPCs, it will go via the transit gateway. So you can say it's like a hub and spoke architecture. There is a one central hub, and these VPCs, all the communication is happening via this central terminal, we can say. So a couple of points. Again, it's a centralized private IP connectivity between multiple VPCs. Again, VPCs must be in the same region as transit gateway. For example, if we have transit gateway connected in US East 1, the VPCs must also be existing in the US East 1 region itself. Again, the VPCs can be in different accounts similar to the VPC peering we have. So transit gateway also supports cross account peering. Next we have the extend an on-premises network into your VPC. So we have these two options which are AWS VPN and AWS Direct Connect. So these are also advanced networking features which will enable us to create a connection between the private data center into our virtual private network into the AWS environment. So yeah, pretty much we had a lot of theory discussion. Now we'll slowly go ahead and continue our hands-on labs from the AWS Management Console. So I'll prompt you to go ahead and open your AWS console respectively. So I'm already inside the console here. So quickly here we'll go ahead and create our first VPC here. So I'll just go and type, currently I'm in the North Virginia region, so which is equal to US East 1, which is a US based region. So I'll just type VPC here, isolated cloud resources, go ahead and click there. So we have the VPC dashboard here. You can see how many VPCs there are existing already. We have subnets here. So I think we already have one VPC here. What I'll do is I'll just go ahead and select a different region, for example US West 2, and let me see if there is a VPC created there. Yeah, it's a good way actually. There are no region in US West region, so we'll go ahead and create our first VPC here from fresh. So we have this overview of the console here. So we have the dashboard here, which is virtual private cloud, your VPCs, subnets, route tables, internet gateways, all the configurations that we can play around with the VPC. We have the security related things, for example, network ACLs we had discussed. We had discussed security groups for allowing and denying traffics or rules, we can say. We have the DNS firewall, we have the network firewalls, we have the VPN, verified access, transit gateways, traffic mirroring, lattice, whole lot of stuff. So just simply go ahead and create a VPC. So I'll go ahead and click create VPC. So for now what we'll do is just create a VPC, that's it. So we'll not select VPC anymore, we'll just hit VPC. So what I will see, we'll just give it a name. So my first VPC. Next what we'll select is, we'll just select, I think, I think IPv4 CIDR block is will suffice here. Will not select the IPv6. So it is about the CIDR blocks. For example, the IP address types we want. So we'll go ahead with the IPv4 here. So the CIDR also will select the larger one, which is class A. I'll hit 10.0.0/. So we can see that the VPC is currently under available state. So you can see while creating the VPC, we only gave the VPC name and the IPv4 CIDR range, and we had set the tenancy to default. I think some tags we created. So we created these tags, the name and the purpose, which is testing. But we can observe that there are a whole lot of things that have come up here. So the first thing is the VPC ID. So AWS creates a unique VPC ID for each VPC we create. So it will be getting populated after we create the VPC. And the next important factor we can say the default VPC is set to no. So in every region, what AWS does is it will create a default VPC. So there will be one default VPC that is already created by AWS, but rest whatever the configuration that we create, it will come under the custom VPCs. So in this case, we can see that it is not the default VPC. So you may be already seeing the DHCP option set here. So it's also kind of random ID. So what this DHCP is, the dynamic host configuration protocol. So what this does is whatever the devices that are connected to this network, it will assign the IP address automatically for that. So this is helpful in assigning the random IP addresses whichever are available to that specific devices connected to this internet. So we also have other options like DNS hostnames, which is disabled, and we have the DNS resolution enabled, which we'll see later. So we have the main route table which is created by AWS in the backend. We also have this main network ACL. So we can see that by default these three are automatically populated when you create a fresh VPC. So I'll quickly go ahead and show you some default VPC which is already existing. I think it's not in the Oregon region currently. We'll just go ahead and go back to the US East. So I can see, yeah, I think this has no names. So if I click on this and come under the details, it says default VPC as yes. So it has been created by AWS beforehand in the North Virginia region. So yeah, this is what I wanted to show about the default VPC status. So going back to our created VPC in US West. I think in the US West, Oregon. Yeah, here is our VPC. So I want to reiterate here that you can see uh, a VPC is always a regional resource and not a zonal resource. In case, for example, zonal in the sense availability zone. So you cannot create a VPC in an availability zone. Always it is uh, designated to a region, you can say. So this is an important point to consider. For example, Oregon, we can have created like we can create the VPC to US West 2, not like 2A, 2B, 2C. Like we can't associate that with the availability zone, we can say. So there are services in AWS like which span from being a global service to a regional service to a zonal service. So in our case, what we can see is the VPC here is a regional service. So it is confined to a region, we can say. Again, we also saw that we didn't specify any availability zone while creating this VPC. So next, what we'll do is we have just acquired some space inside the AWS by creating this VPC. Next, if you want to connect this, for example, we can make the communication happen like under this VPC if we create some resources, and if the resources have a requirement of internet access, they want to communicate with the outside world, then we need something called as internet gateway. So what this internet gateway will help us achieve is it will help the resources inside this VPC to connect with the outside internet. So without that, it is not achievable in the AWS. Also, one important thing we have is there is only a symbiotic relationship, we can say like a one-on-one relationship between a VPC and a internet gateway, we can say, because only one VPC can have only one internet gateway, and simultaneously one gateway can be attached to a one EPC at a time, we can say. So we'll quickly go ahead and create an internet gateway to attach to this VPC. So I'll go to internet gateways. So there are currently no internet gateways found in this region. So what I'll do is I'll go ahead and create internet gateway here. So I'll just type IGW-1, which is my first internet gateway. So tag I will leave as defaults. So I'll go ahead and create it. So we can say it's already been created, but the state is detached here. So initially we can see the state is detached. We have the internet gateway ID populated, the VPC ID is not, since it is not attached to anything. So what we'll do is under actions, so I'll click attach to VPC. So under here I'll select the VPC which we have created, which is the my first VPC. Go ahead and select this and hit the attach internet gateway. So we can finally see that the status is attached. So again, if I go to my VPC, uh, under resource map, we can say like resource map is very interesting feature actually. It will give a whole lot of flow of how the things are existing in the network. We have the VPC and my VPC. So there are no subnets here. So we have one default route table automatically created. So under network connections, we can see that IG1 is populating, which is our IGW, which we have attached, which is the internet gateway. So since we have our VPC and internet gateway sorted, so we need to understand another concept called subnet here. So imagine VPC, you already saw it has a bigger room. So under like bigger house. So under that house, we can partition the house has rooms, right? So rooms means smaller partitions or chunks of that bigger house. So what subnets help us is it will help us segregate even finer with the within the VPC. So VPC is a bigger house, so subnet we can see that has a subset of that VPC. So we can again make an isolation of various IP ranges. So here we'll go ahead and create the subnet. So we need to select this VPC. So I'll select my VPC here, my first VPC. So associated VPC headers is it will inherit from the parent VPC that we already have, which is my first VPC. So we had selected this 10.0.0.0 slash 24 earlier. So we'll give the subnet name. So my subnet 1 will be the name, and availability zone. So since we are already in the Oregon region, which is US West region, we can see there are four availability zones. So there is US West 2A, US West 2B, US West 2C, and US West 2D. So I'll go ahead and create in the first region, first availability zone. So one more concept is the concept of CIDR block here. So always make sure that it is in the same CIDR block of the parent CIDR block, because if I since we have selected this, and in case for example I'll go ahead and select a 20.0.0.0 slash 24. Always ensure that we need to give a valid CIDR block. So we'll go ahead and give a very familiar what we can say a CIDR block which will align with the parent CIDR block. Dot. So selected as it is 24 only. So key name and will leave it as default, and I'll go ahead and create the subnet. So you can instantly see that our subnet has been successfully created. So we'll go ahead and create again a private subnet. So I'll go ahead and create subnet again. I will select the again my first VPC. I'll give the subnet name as a private subnet. Availability zone I'll actually ignore it for now. So CIDR block again I will leave it as it is. For example, I'll just copy paste. So again I'll go ahead and create the subnet. I think it will overlap, so we'll just select one here. So let us choose a slash 26 or 28 here. Slash 28. What we'll do is I think we have overlapped the subnets, so just ignore this and we'll freshly create new subnets quickly. Just go ahead and delete this. So freshly go ahead and create a new subnet. So keep in mind that we need not have any overlapping IP addresses. I just go public subnet here. Availability zone will be again 2A. So CIDR block I'll select as 10 dot 0 dot 0 dot slash. Go ahead and create the subnet. Again, create a new one, selected VPC, again this one, my first VPC. I'll name this as a private subnet for the private one. Availability zone I'll ignore. So we'll just select 10 dot 0 dot 0 dot 0 slash. Maybe I'll just take a 64. I think that this should work now. This is for the private subnet. Yeah, now we are sorted with the subnets. Just go ahead and create. So we have one public subnet and one private subnet now. So you can see that we have successfully splitted the CIDR ranges, and we have 59 IP addresses available. So we can also see like the availability zone it has selected by default, even though we have not specified it, is the US West 2A. So it's a good thing. So rest all I think we can ignore for now. Just go ahead and hit the subnets. Since we have named public and private subnets, but we can just go ahead in the public subnet. I'll click this and go to the route table. I can see that there is no internet gateway attached. So this subnet is not at all connected to the outside internet. So whatever resources we create under this public subnet, for the namesake it is named as public subnet, but there is no route table IGW explicitly attached, so that I think a resources created under this subnet can communicate with the outside internet. So what we need to do is we need to attach a IGW here, which means a internet gateway. So we'll make this fast now. Observe this carefully. So I have selected the public subnet here and also the route table. So this route table actually was associated with the VPC. So by default, it will attach to the subnet as well. So we'll go ahead and click this route table here. So we'll again select this one, the default route table, and under here I'll just maximize this for greater visibility. We have the details of the route table. So under routes, we only have this destination local, which is just the VPC CIDR range. So now what I'll do is I'll go ahead and hit edit routes. So what we must do is we must go ahead and add route here. We need to select 0.0.0/0, and then again we need to do the internet gateway here. So internet gateway I already have created one, IGW1, we can see previously. So I'll use this. Go ahead and save changes. So it says updated routes. Now we can confirm that the subnet is a public subnet. Now we have successfully made our subnets public by actually attaching the internet gateway. So just we'll cross check whether like it is attached, our route table is attached to both the subnets. So public subnet is fine. So now we'll go to the private subnet. I'll click on here and go to the route table. We can see an anomaly here. It's again in the targets. We can see the internet gateway. It means under the subnet, private subnets route table also we can see the internet gateway being attached as a route. So now what I will do is to make this subnet actually private. So what I'll do is we have something called route tables. So since we have only one route table, what I'll do is I'll just create another route table. I'll mention it R RT private, and you VPC, I'll select my VPC and just create the route table. The route table is successfully created, and when I go to subnets, I just select the private subnet, and under route table, uh, not here, under route tables. So I have created this RT private, and we can see this option as subnet associations. So means we can have the provision of attaching this to a subnet of our choice. So I'll just do a edit subnet associations, and I'll just attach the private subnet and just do a save associations. So yeah, now we can see that it's successfully attached to the private subnet. So when I hit private subnet and under route table, so you can see that the route table has changed to RT private here, and in the public subnet we can see that the route table is the default which was created earlier, which is 4AC85. So this is how we can play around with the routings with the help of route tables. So with this actually we saw and played around how to create a VPC, how to create subnets, how to create route tables, how to attach an internet gateway and all. So we'll demonstrate something called as peering connection between two VPCs here. So we'll just go ahead and create another VPC quickly. So it will be my VPC2. Cider, I'll select something between 10.0.0. Slash tenants will be again default. I'll just go ahead and create a VPC. So again I'll create subnet. So I'll go ahead and create a subnet here. My VPC2. CIDR I'll give as again 10.0 slash 18. So I'll create subnet. So again we'll do a route table here. So we can see that since we have created 3 route tables, we can already see like 2 are default and 1 is created by me, and internet gateway is already only one here. So I'll just create another internet gateway. So I'll name it IJW2, create an internet gateway, and I'll just actions attach to VPC and I'll attach to the second VPC. So as you can see, only one internet gateway can be attached at a single time. So we are sorted with it. Now what I'll do is I'll just go ahead and create some resources under this VPC. So I'll go to EC2, just go to EC2 here. I'll just go ahead and launch an instance quickly. Just type instance 1. Use the default AWS Linux ones. T2 micro. Key pair, I'll not create a key pair for now, since we are just demonstrating VPC peering here. So I'll just allow the HTTP and HTTP traffic from the internet. Just go ahead and launch the instance now. I think, yeah, we launched this under the my first VPC. I'll go ahead and launch instance. Okay, again I'll launch a second instance in the second VPC. I'll name it as instance 2. I'll leave all as defaults. Again, I'll proceed without a key pair, though it's not recommended, but for the sake of this demo that we are doing, AWS and public IP, I'll enable it. So security groups I'll leave as it is, and just go ahead and launch. Okay, it's not supported in 2D, so what we'll do is we'll change the instance type here. Seems so. Let me select T2 medium, all generations. We'll just go ahead and select a Ubuntu one. So instance type, for example, I'm creating a different subnet in US West 2B so that there are some supported instances available. So I'm going ahead and creating a instance 2. So I'll allow HTTP and HTTPS traffic from the internet. So we'll just edit the network settings for now. Auto send public IP I'll enable. I'll leave rest of the things as default and I'll go ahead and launch the instance. So we'll wait for some time. So I have two instances, instance 1 and instance 2, which are in two different availability zones and in two different VPCs. Now since we have created two instances in two different availability zones within a region, so we'll see how we'll go ahead and create a VPC peering. So I'll go ahead and type VPC. So between these two VPCs under the same region, we'll see how to create a peering connection. So we have something called VPC peering. Yeah, we have the VPC peering connections here. So let's create a peering connection. So I'll say save it something like peering connection. Peering VPC will be fine. So the requester will be my first VPC. So we have a couple of details. The VPC CIDRs we have, and it will ask two things: the account, which is the my account or another account. So since we are using my own personal account, we'll use the my account, and the region will be this region itself, since we have all the resources here itself. So we have the provision of cross region pairing as well. So if you are having VPCs in another region, so you can go ahead and select the appropriate region from that as well. So the acceptor in our case will be the second VPC, VPC2. So tag I will leave as it is. So it says, so it's very important to observe that a pairing connection cannot be created between two VPCs that have overlapping CIDRs. So we'll select another VPC which will have a distinct CIDR. So I'm going to create a new VPC which will not overlap with the existing CIDR. So I'll go and create a respective subnet as well. So I'm again going to create a new subnet here. So we'll try freshly here about pairing connection. So the requester will be first VPC. So we'll leave as it is. So the acceptor will be the second one. And just go ahead and create a pairing connection. So it says a VPC pairing connection PCX pairing VPC has been requested. So now what we'll do is, it's saying pending acceptance. Since we are in the same region, no need to go ahead and change the regions. So I'll just go ahead and click accept. So now we can see that the status is active. So we have the request owner ID and the peering connection ID. So this is a peering connection can be done between two VPCs. We have the possibility of doing cross account VPC pairing, cross region, cross region, single account, multiple combinations we can achieve here. So this was all about the pairing connection. So now what I'll do is I'll just go ahead and delete the pairing connection, and we'll see how we'll actually go ahead and create a transit gateway here. So it's deleted. Now we have transit gateways. So similarly, we'll go ahead and create a transit gateway. Just give tgw1. So there are some defaults we can configure. So we have this DNS support, we have VPN ECMP support. So similar to the VPC creation, when where like a route table is automatically created. So what happens is when you create a transit gateway, again a route table is associated with it as well. CIDR I will give as 10.0.0.0. I'll just go ahead with 24 and I'll go ahead and create the transit gateway. So transit gateway always takes some time actually, since it's a very huge resource. Actually it will take around couple of minutes. We can observe under the state about its status. So again a ID similar to a VPC ID is populated again, and we can see all the different, like the state is still in pending, the owner ID, the transit gateway ARN. We have the route table which is already created by default. Successfully we can say that the transit gateway is available state now and is getting ready to use with the VPCs we have. So this was all about the hands-on session. Now quickly moving to our uh, couple of things, like final, we need to see the best practices that we need to follow. So the first thing is the virtual private cloud related. So it says use separate VPCs for different environments, example production, development, testing, to isolate resources. So it's always a good practice. So you name and tag the VPCs properly. For example, purpose you can say as production, development, or testing in enterprise environment, so that no one gets confused whether it's for testing or it's a live production environment. So also we need to design VPC CIDR blocks carefully to avoid IP range conflicts with on-premise networks. So as we saw, like in couple of moments while I was using it for peering or with for example normal subnet creation, we used to see like cider range overlapping. So to avoid that, always be careful with the notation of the IP ranges. So one VPC must have a different IP range and another VPC must have a different IP range. Also, we need to leverage multiple availability zones within a region for high availability. So always take use of the multiple availability zones so that our workloads are fault tolerant and ready to uh, make them disaster proof. Next is the subnet design. So we need to create public and private subnets for a multi-tier application architecture. So always make use of these public and private combinations. Also we can place resources that need direct internet access in public subnets and backend resources in private subnets. So only resources which require direct internet access. So with the help of IGW, we can make them available via public subnets, and any backend resources like databases which are not like internet facing should be in the private subnets. Also we can use NACLs to control inbound and onboard traffic at the subnet level, and also we can leverage security groups as well. So yeah, as I said, security groups is also an important part, so we should always make use of them to define the inbound and outbound traffic at the instance level, so that there is very fine grained access available and no outsiders will enter into our environment. Also follow the principle of least privilege, allowing only necessary traffic to and from instances. So use IAM also, so that a developer is given only the developer activities related permissions or something kind of that. Also route tables we can configure route tables to direct traffic between subnets and to the internet. So necessarily as we saw regarding the internet gateway, we can accordingly edit the routes. So internet gateway and NAT gateway, again we can attach an IGW to a VPC to enable internet access for instances in public subnets as we already saw in the hands-on. And also we can use a NAT gateway for instances in private subnets to access internet without exposing them directly. So yeah, this was all about the best practices. Thank you for attending the session and hope you understood a bit of networking related aspects of the AWS. So we saw about AWS networking related aspects like VPC, subnets, route tables, IGW, which is the internet gateway. We did a VPC pairing and also we created a transit gateway. And in the next session, we'll be discussing the AWS domain name system, which is AWS Route 53. Again, thank you for attending the session and hope to see you in the next session. Bye.